I'll take you through some brief introduction of IEEE and Power and Energy Society. So IEEE is the biggest engineering organization in the world with more than 420,000 members. We have 39 technical societies, of which PES is one of them. So you can see the green circles. This is PES, with more than 38,000 members globally. We have a lot of good things to offer to power engineers, including publications. So many good publications. So IEEE Power and Energy Society and PS transactions and electrifications. If you're a power engineer, your membership dues, you pay for the magazine itself. I think it's worth than the membership fee. So, but there are more. There are a lot of benefits for becoming a member. IEEE gives you a network of access to best power engineers in the world. I want to also tell you about this conference that we have in Thailand. Mark these dates in your calendar, 19th to 23rd of March. This will be the first huge event outside North America. You know, they have IEEE PS general meetings. So this is a sort of event, but in Thailand. A big shift in power. We are expecting to have 5,000 attendees in this conference. Would be good for you to also attend, and also would be good for you to join us. But let's introduce our speakers for tonight. Pierluigi Mancarello. I actually looked at his credentials and his biodata, and I tried to summarize, but I couldn't summarize. I think I need to read it as it is, because they're so important. There is nothing, you cannot say. So Pierluigi is a chair professor of electrical power system at University of Melbourne currently, and part-time professor of smart energy systems at University of Manchester in the UK. Pierluigi obtained his PhD in electrical power systems from Politico di Torino in Italy, and has been a research associate at the Imperial College in London, and has held visiting research positions at SINTEF NTNU in Norway and NREL in Colorado, as well as a visiting professorship at École Centrale in France and University de Chile. Pierluigi has been involved in or led in the last 10 years some 50 research projects and consultancy and professional activities in the UK, Europe, Australia, and internationally in the area of techno-economics, of smart grid technologies and distributed energy system, risk and resilience assessment of future networks, integrated multi-energy systems modeling, and energy infrastructure investment under uncertainty. Pierluigi is the author, editor of 4 books, several book chapters, and over 200 research papers. Well, he's very young, you will see him. He is an editor of IEEE Transactions of Smart Grid, the IEEE Systems Journal, and the International Journal of Electrical Power Systems and Energy Systems, as well as guest editor of Philosophical Transactions of Royal Society A. So if you're interested what that is, maybe you can chat to him afterwards. Pierluigi is an IEEE Power and Energy Society Distinguished Lecturer. That's why he's here tonight. The past chair of Energy Working Group of IEEE European Public Policy Initiative, and led the Melbourne Energy Institute work Power System Security Assessment of the Future National Electricity Market, commissioned by Dr. Alan Finker, the chief scientist. So please put your hand together for Pierluigi Mancarello.
Thank you. Thank you very much for the very kind introduction. It's always a bit embarrassing to actually have someone read your bio. So it's a great pleasure to be here. I'm impressed by the audience. I'm very actually pleased to see all these people. I appreciate that the weather is helping me, and I apologize because everyone is telling me that I brought it from Melbourne. But that's not true because I'm coming from Europe actually. It was very sunny in Italy. So can't blame me, but I'm sure that it will pass soon. So what I thought I would tell you about today is a little bit of the work that we're doing on reliability, and a little bit I will touch on also resilience of future energy systems, particularly motivated by the work that Dean was mentioning, were commissioned during the Think Review. However, we dress it up a little bit more like a lecture, because we professors love lecturing, and probably give a little bit of insights into also future aspects of energy systems, role of new technologies, some of the new technologies. And before starting, two more things. One is there's also the Law of Manchester, because I'm still a part-time professor there, as you heard, and much of this, or some of this work is coming actually from what we did and we're doing at the University of Manchester. And you want to know about the Philosophical Transaction Royal Society. That's actually the first journal in the world. That's where Newton, Maxwell, and so on published. So I thought it would be interesting actually to be an editor in a journal that is 400 years old. So yeah, that's what it is. Now, these are the points I wanted to cover, in more or less different extent. I'll give a little bit of context while we're doing this work, and a little bit of trying to make systematic, to have any systematic understanding of the role of renewables in terms of technical aspects and impact then on economic aspects and market aspects, and how there is actually a tight interaction between the two. Then just mention South Australia Black System event, because we can't do without this, talking about sorts of issues. And then a little bit more of fully interesting aspects of future energy systems, as I mentioned. But now, before starting, the question is, are we worried about delivering a zero carbon energy system? And if yes, like, why are we delivering? Well, if you talk to people around, probably they're saying, not at all, we're not worried at all. Have wind, we have solar, so certainly we know how to do it. Then if you talk to IEEE, they will actually be pretty scared, I'm sure, because we know that there are a number of issues that have been brought into the system. And the reality is that then if you look at markets, you look at economics of the system and so on, things are actually not as good as they might be, as one would expect. In fact, that's why we talk about the energy trilemma, which is basically how we would be able to deliver a low-carbon economy, a low-carbon energy system that at the same time is affordable, secure, reliable, and green, of course. Now, why is this so important? This is important because effectively this is disrupting the way that we have operating designed power systems last 100+ years, which effectively were designed and operated as a trade-off between affordability and security. So you want to keep the prices or the cost in general low, but you also want to keep the lights on. So you think about it, it's being a trade-off between security, reliability, and cost. More expensive, more secure. And you want to find the right trade-off there. Now, the moment that you want to decarbonize the energy system, particularly through renewables, this has got big implications. And we see that these big implications are for both the sort of economics of the system and the reliability of the system. However, what is a little bit less clear is how actually one is interacting with the other. So if you think that the connection between decarbonization and markets and reliability are pretty much obvious, actually you will see how their interaction is a lot more complex than you might think. Of course, the main main problem here that we'd like to touch upon is that of reliability that has got different aspects. Starting from aspects, of course, of flexibility, and just to mention something here, these are Mickey Mouse examples, really taken away from lecture slides. So we say if I have a system that would dispatch without wind, and there is also a bit of nuclear here, not the Australian case, but general case, then the moment you introduce wind, you will know that there are minimum load issues. Where actually you start having some problems here with the net load being, for example, smaller than minimum stable generation of inflexible generators, and you have very, very high ramps up and down potentially in terms of net load, which in this case is defined as load minus renewable generation. Now, what I would like to point out here is that this corresponds also to a reduction in the capacity factor of conventional power plants. Now, I am learning these days that the system in Western Australia is pretty different in terms of energy market from the system in NEM. However, these are sort of general aspects that apply to many systems around the world. It is intuitive anyway that the more energy is produced by wind, the less will be produced by conventional generators, and therefore the overall output and then capacity factor will decrease. Similar aspects are associated with the so-called DAC curve. I'm sure you've seen this quite a number of times already, and probably you will see the DAC curve here in Western Australian system as well. If you look again at net demand curve, load minus, in this case, photovoltaic generation, you look at increasing penetration level of solar. Solar energy will eat up more and more of the net load demand during the central hours of the day. However, still there is a requirement to cover the peak. So this has got lots of implications again for system reliability and security, depending on how you interpret that. Because of, for example, the considerations about the high ramp that conventional generators need to take up to cover the peak demand that hasn't changed, especially if you look at days like spring days, for example. This is coming from California, typical spring day with lots of sun, but load not so high yet because air conditioning systems are not fully on yet. But there are also other issues that I learned actually this afternoon already happen in terms of commitment of generators, level of inertia and so on, which I will discuss a little bit more later. However, another common point with the previous picture about wind is the fact that also in this case there is certainly a reduction in the capacity factor of conventional generators. So again, all this energy that before was produced by conventional generators now being produced by renewables that in a way are coming at close to zero marginal cost. In a way, therefore, in a way or in the other, we have dispatch priority in the market, assuming that there are no network constraints and things. Now, what's happening there then in terms of impact of this? There are basically technical issues, but no, they're projecting in terms of cost functions. So if we look at capacity factors, lower capacity factors means higher average cost of production. Average cost of production in this case is including the fact that conventional generators would have to recover their investment. So obviously, the more they can produce, so the higher capacity factor is, the lower the average cost will be, because basically they can spread the investment cost over larger production. At the same time, market prices go down. That's why we introduce renewables. We would like to see energy prices going down. What does it mean? Well, it means that effectively their ability to recover the fixed cost decreases. Why is it so? Well, because again, whatever they bid at, on average, the market prices would be a little bit depressed. So on the one hand, as you can see, the average cost of production is going up. On the other hand, the ability to recover the cost of production is going down. Now, what happens next if we look at basic technical economics of the system? Well, you can imagine we'll see in a second. Further to that, and now, and this picture is being designed on purpose for the thinker review to explain the issue of higher low inertia to achieve scientists. When we look at a system where there is less and less rotational energy available coming from conventional synchronous generators, if we look at the classical frequency response curve in response, for example, to a loss of generation, if the blue is the traditional response, conventional response, given, let's say, the current level of inertia, rotational energy of synchronous generators, the moment that we decrease the amount of synchronous generation in the system, there would be quite some effect on the potential frequency response of the system following a contingency. For example, the rate of change of frequency will become a lot higher, so the frequency will go down much faster, and the frequency nadir, so the minimum level achieved reached by the frequency, will be lower than before, potentially a lot lower, and will also happen earlier than before, which means that the sort of protection devices and all the means we have in place to recover the frequency effectively got less time to react. I will comment later on this aspect. So, having all of this in mind, it is intuitive to understand that we start losing more and more synchronous generators from the market. These synchronous generators are, looking at this specific case or provisional security, the ones dealing with frequency response, for example, then we could be in trouble. In fact, what happens next? Well, what happens next, and we've already seen it in the past. And what do you think will happen next? That's what happens next. And now, just to keep you a little bit awake, actually, it's very sad to say this. But something that I wanted to point out is the fact that I'm not prepared these slides for the thinker review. Well, the previous slide, yes. But in general, this set of slides, not coming from my experience in Australia after the blackout. These slides are coming from my lectures in power system economics and smart grid and sustainable energy systems in Manchester, and they are 6 years old. So 6 years ago we were teaching this and trying to understand, try to really identify sort of interactions between security, reliability, economics, and renewables. And in a way we were all expecting that sooner or later this would happen if the market were not correct, something that was happening. In fact, it happened. But what is so challenging? I mean, it's really so challenging. Now, why have I put here the slide of the moon landing? Taking this from my supervisor, ex-boss at Imperial College, Goran Strbac, great professor. And he used to say, if engineers sent the man to the moon, they can do big magic. So certainly delivering a low carbon energy system is not a problem for engineers. So but they do need something. What do they need? Well, money. We sent the man to the moon, but the budget was infinite. Now, what we're talking about now is not an infinite budget, and in fact, that's why we talk about techno-economics of energy systems. Talk about techno-economic problem is never only a technical problem, because that can be solved. I'm sure that in this room there are enough and smart people to really solve technical problems, and could give them the money, problem solved. So it's really a technical problem how to solve the problems within a certain market, commercial, regulatory and policy environment. Now, said that the problem is not technical only, but it's a techno-economic problem, then the two concepts need to be dealt with together. Let's try to go back to the fundamentals of power systems and try to understand some way forward. So, One aspect is the fact that one of the problems is that flexibility in broad terms, and I would say also reliability with security. So all control power systems currently is coming from the transmission network. So effectively the distribution network is inflexible, very inflexible demand, very little control here, and all the flexibility and ability to control power flows and to provide security is coming from transmission systems. So obviously the less we have in here able to provide this control, this security, the more in trouble we are. And again, we think that this is a far ahead future, no far away. Well, put here the picture taken from my news report about the separation of the two systems, South Australia and Victoria, during the Black System event of September, that you know pretty well, where there were a number of events following very extreme weather, unexpected response of the protection systems of wind turbines, causing overloading of the headwood interconnector, probably a number of instability issues anyway, and then the islanding of South Australia, with very little synchronous generation available, and therefore the collapse of the frequency. In fact, the moment that you island a system with little synchronous generation in the system, what happens is that this rate of change of frequency, which can only be limited by the amount of rotational energy that is available in synchronous machines, so effectively how much synchronous capacity you have running in the system, then, well, this rate of change of frequency can become really, really high. And in fact, during the blackout, the estimated rock-off was in the order of 6-7 Hertz per second. And it is believed that the frequency dropped to 47 Hertz in 0.2 seconds. Obviously, there is no protection that can really respond this fast. Maybe, most probably not even batteries today could be able to respond to this, and inter-trip schemes, system integrity protection schemes. I mean, everything that we know is very, very fast. We'll probably be in trouble with this kind of event. So the Black System event, in a way, was really a sort of demonstration of how those reliability issues associated to the fact that you have lots of renewables in the system, as well as less synchronous generation available, very much also because synchronous generators are retiring from the market due to economic issues. Well, all of this basically has been exemplified in the Black System event. That's why I call it, in a way, a textbook example. I'm sure that when we write books in the future about our system, certainly this would be mentioned and as one of the first really highlighting of this theoretical aspects. Now, from a research perspective, and then, of course, immediately together with that, from a operational perspective, the question is, what comes next? What do we do actually to deal with this? Do we need a stronger, a bigger, or smarter grid? Where by stronger, I mean, for example, we reinforce the system different ways. By making it bigger, we add redundancy. Basically, imagine we mesh more the system, and or we make it smarter. We introduce a number of new technologies and control strategies in place. Of course, all of this is, again, it should come from a cost-benefit analysis. We look at effectiveness of different interventions against cost, and then depending on the specific case, you can be in one of these regions, or maybe you will be in different regions. So this one was exactly sort of question that we were given by the chief scientist when we were commissioned this study that was mentioned earlier by Dean, the security assessment of the future national electricity market. So during the thinking review, they were analyzing a number of future scenarios. However, they were not analyzing this from a point of view of reliability, security, and so on, only from an economic point of view. So what are sort of optimal level of investment, new portfolios. So the question that actually the Minister of Energy asked to chief scientist was, how do I know that these future scenarios they're putting forward actually won't cause another blackout? And then the chief scientist came to us asking the same questions and looking at the ways that we could to make the system secure, even with more and more renewables into the system. This, of course, is associated with this picture that I said I drew specifically to demonstrate the basic concept to chief scientist, and particularly looking at the fact that when you change the level of inertia in the system, so when you change the amount of synchronous generation that is dispatched in the system, the dynamics of the system response will change a lot, particularly, as I said, in terms of Rokoff and nadir. However, what is important to notice is that this is a quasi-steady state frequency value, which is basically the value that the frequency achieved after the governor response to generators. Well, this doesn't change, it's the same. So why it doesn't change? Because effectively this is a function of the primary frequency response, or in other words the governor response, that is available in the market. And if you look at the market system, if you look at the market environment, basically this picture says that if you size the frequency response in a certain way, then steady state you will be reaching this level. That's how the frequency response sized is sized actually in the market. So if you look at the ways that the 6 seconds frequency control and serial service market works, if you look at the way that the frequency response is sized, is basically based on the so-called quasi-steady state frequency value. It's not written there, but we know from power systems that it is like this. So the argument here is that if you keep sizing the frequency response and looking at this parameter, actually that way of sizing doesn't take into account at all the level of inertia. So in quasi-steady state value, you always think that you are okay. However, if the level of inertia changes, then your Rokoff, your nadir could be very, very different. And potentially, you might not realize that you will reach a point where the rate of change of frequency can become very high, the nadir can become very low, and so on. So the question is, do we have a systematic way to make the system secure? And to do this, we introduced the concept of frequency response security maps that is illustrated in this picture, and there are more explanations on the route as well. Now, what we summarize here is a very sort of simple and basic thinking approach that power system engineers will have, together with a little bit of optimization theory. So the idea is, if the current system is sized based on this, this is, by the way, in this map, I showed the primary frequency response available in the system against the system inertia, post-contingency system inertia in the system. So if the current market is sized, the frequency response in the current market is sized in a way that corresponds to this horizontal line, if I have problems in my head, I may have problems in the future also with other constraints, why don't I design sizing of the primary frequency response also to actually take into account the other parameters? In other ways, this is okay, this is these horizontal lines, but if I know that dynamically I can have problems with the rate of change of frequency and the minimum level of frequency nadir, why don't I formally constrain the rate of change of frequency and the minimum level of frequency nadir to values that I think are acceptable for me? So for example, if I do not want to have a rate of change of frequency that is higher than 1 Hz per second, can I write mathematically a set of equations that can actually be implemented into the dispatch engine to constrain the Rokoff to the value I desire? And if I do not want to have a frequency nadir lower than 49.2 Hz per second, for example, before you start shedding loads and so on, can I mathematically write a set of equations, again, I can implement into the dispatch engine so that no matter what happens, I know that the frequency won't go lower than that? that's exactly what we did here. And when you plot this set of constraints on this plan, I said the quasi-steady state constraint is this horizontal line, and it is independent by definition of the system inertia, and that's why we don't know actually there is a problem today, because the market doesn't measure inertia, so we don't really know if there would be a problem. Then there is the constraint on the inertia level, which is a vertical line, because this constraint does not depend on the frequency response, the power frequency response, only depends on the amount of synchronous gyration it is in the system. This is because we assume that when there is a problem and the frequency goes down, it's going down so fast, at least in the first instance, that actually the governors of generators cannot react yet. So the only way of constraining the rate of change of frequency in the initial instance is to actually constrain the inertia. And then the red curve, which is hyperbolic if you look at the mathematical function of this, is actually the expression of the frequency nadir. So through this curve, you can actually introduce the constraint that is telling which area you can operate so that the frequency does not go down, or below 49.2 hertz, for example, depending on what parameters you would use for that. So when you look at all the sets of constraints together, the envelope is actually generating a secure area. So if I operate in any of this gray, in any point of this gray area, I can say I am secure because I am meeting the constraint on the quasi-steady state frequency response value, the inertia constraint, and the nadir constraint. Now, why is this picture important? Well, the most important reason is just probably because it's intuitive. And engineers are simple people, So like this, actually, you can identify very quickly what you're talking about. It's like, okay, I'm operating here, it's secure. I'm operating here, not secure. The other one that I really find very interesting is the fact that by this, you have, at least I want to think I have, a formal way of defining what is high inertia and what is low inertia. Because if I ask anyone, what is high inertia, what is low inertia? When do I change from a high inertia system to a low inertia system? Can someone tell me? So, our thinking in this respect is the following. Look at what happens here. So in this interval, which corresponds to high level of inertia, the binding constraint, so the first constraint to be active, is the horizontal constraint corresponding to quasi-steady state frequency value. So actually, this is what happens in the market. So this constraint is more binding than the constraint on nadir. That's why we don't see that there is a problem, because actually, with high level of inertia, with all synchronous generators, for example, the market is doing the right thing. You must size the frequency response based on this constraint. The problem is that when the inertia level goes down, there will be a tipping point where now the constraint that is active switches to the nadir constraint. This is the tough one that you do not identify, because if you keep sizing the primary frequency response based on this, for example, operating in this region with this level of inertia, what you will not realize is that you do not have sufficient primary frequency response to actually recover the frequency. So if you're still sizing your primary frequency response based on the quasi-steady state frequency value like it is done today, you will probably miss a big chunk of governor response available to recover the frequency. The moment that there is this switch between one constraint and the other, that's what we call now low inertia system, because then what we've done for 100 years doesn't work anymore. That's our sort of definition of low inertia systems. Current system is defined with the primary frequency response on steady state level. The future system, we have to introduce a new set of constraints that can become more binding than the constraint that we used for 100 years. And that's sort of corresponding to. So based on this is just the graphical representation of the thinking. Now it is, how do we incorporate this into an operational tool that potentially we could embed into IEEE's dispatch engine? Now, there is a little bit of mathematics there is a little bit of modeling, there is a little bit of optimization, or it's a little bit things for which it's good that we still have universities not doing something interesting, I would have to say. So we developed this modeling that didn't exist before, which we called a frequency response security constraint optimal power flow, where basically we took the fundamental equations that are very similar to what IEEE uses in their dispatch engines, and we introduced a new set of equation constraints, still maintaining the problem linear or mixed integer linear if you also included some unit commitment in there, so that it could effectively be incorporating the dispatch engine if we wanted, but at the same time take into account the new sets of constraints on the rate of change of frequency and the nadir. So what you now have when you look at, and of course all the network power flow constraint or classical things of classical optimal power flow. So what now the model gives you automatically is a co-optimization of energy and FCAS, which is what the linear co-optimization model of IEEE does today, as well as inertia. So now inertia becomes a variable of the problem, and the model automatically dispatches at the same time energy FCAS, particularly primary frequency response, but more than that actually. In the model we dispatched all the current, the 6 current FCAS, or the contingency FCAS, and the level of inertia. In other ways, inertia is just a form of frequency response. It's just that it's faster. However, mathematically, it is not different from having a governor response. It's just that this inertia is coming from the physics of the synchronous machine, and it's a lot faster and follows a certain physical characteristic, which is the energy that is injected automatically into a system following a loss of generation, whereas the FCAS is the response that needs to be triggered by governors. But in principle, it's all the same. It's energy that you are injecting into the system. So it's all about understanding how to mathematically put in such a way that you find the least cost, I would say, results of all this problem. To give you an idea of how this thing works, if you look at this, simple case, where you would see in blue is the net demand, and in green you have the level of renewables that are dispatched in the system. For example, looking at this region, you will see that there is lots of renewable and very, very little net demand. So you can imagine there will be a very little inertia available at the time. And in fact, what the model does is it would dispatch such a level of inertia and then saturates. So it say you can't go below this level of inertia, because if you go below this level of inertia, I'm not able to actually securely dispatch the system. And at the same time, I dispatch more primary frequency response. So the model automatically says, you have very little load, net load, higher renewables in here, so you need to dispatch more primary frequency response, and you need to constrain the minimum level of inertia that you are in the system. So everything that is now done in several parts, actually, of the world through heuristic rules, say having a certain number of synchronous generators available in the system and all that. So the model does it automatically in a formal way by co-optimization of the system of the equations. And effectively, and you see this very, very clearly, I say, can't go down this level of inertia, but at the same time I need to increase the level of primary frequency response. And again, in a similar situation here, you see again that you constrain the minimum amount of inertia and you put in there more frequency response. Same time, if the demand goes down, but also the level of renewables goes down, then I can actually dispatch in a different way inertia and primary frequency response. It also depends on how much energy I have in the system and so on. So effectively this corresponds to operating in this region where you now basically need to take into account the nadir constraints that there was the one that was active, and if you only use the one constraint, the inertia constraint, or the quasi-state frequency constraint, you will probably not be able to dispatch the right amount of primary frequency response in the system. Now, the model is actually a little bit more elaborated than that, because it also takes into account, potentially, the contingency level as a variable. Say, you should talk to National Grid in the UK about it. National Grid just said, look, I do not care if you want to have 2 gigawatts of nuclear in, say, 2025, because then if I have to size my primary frequency response based on your 2 gigawatts nuclear, I would rather ask you, when there is very little demand, maybe during the winter, to ramp down nuclear. So why would I have to oversize my primary frequency response, get into trouble, when actually you can, for example, bring down your level of generation? So this sizing of the contingency level actually corresponds to ask a generator, if the generator is the largest contingency, to ramp down. If the generator is the interconnector, this corresponds to constrain the power flows in the interconnector. Is this something new? Well, that's exactly what IEEE did. Immediately after the Black System event, what did they do? First thing they constrained the power flows in the interconnector. They did it to limit the rate of change of frequency that you could have. Actually, with kind of modeling, you can do it in very general terms to constrain all the potential, all the parameters of the frequency response. And you can do it again in a formal mathematical way. Now, after all this work, you know that there were the thinking review recommendation coming out, particularly looking at minimum level of inertia, adequate dispatchable capacity, which also means basically you need to have sufficient frequency response in your areas to be able to bring the frequency back, and so on. So there have been quite an uptake of understanding, at least, of how the technical model could be translated into practical recommendations. Now, looking forward, as I said, the question was, how do we do in the future? How do we change the system? We're still relying only on synchronous generators, and what if they disappear? What would they do? So the idea is, if we said that in the future we have trouble because the generators providing here the flexibility will disappear from the system unless we find the new generators being able to provide them, for example, synthetic inertia and all that from wind turbines, but I'm not going to touch on this. Maybe one of the way forward would be to look at different system architectures and the fact that there are a number of new technologies that are coming up in the system. Where are these technologies coming up? Well, obviously they're coming up in the distribution network. So we have PV, we have more and more batteries, we have in the future electric vehicles and so on. So all these technologies that they are active technologies, they are making the network more active, are being aggregated, or we're looking more and more into aggregating these technologies in, for example, microgrids, and then potentially they could interact with the transmission system to actively provide services. So this is the concept that you heard a lot of virtual power plants. So it's not just the aggregation of technologies to, for example, play in the market. There is a fundamental concept that is telling me, if synchronous generators are disappearing from the system, can I find the equivalent of synchronous generator something else? I don't mind if it's not a synchronous generator, as long as those resources look like synchronous generators for the stability of the system. So it's really a technical concept before being a commercial concept. And in fact, if the system is becoming more and more inflexible at the level of the transmission system, why? Because I have fewer generators that are dispatchable, and I have more and more wind and solar farms in the system. Well, why can't I find the flexibility in here? In a way, that's the only way. It's not the only way. I mean, as you know, from IEEE's integrated system plan, there is lots of interest in still these renewable energy zones where we have large-scale renewable generation, possibly associated to dispatchability and security concepts in the zones. For example, would be having batteries and so on. So there are certainly other ways of doing this. However, this is of particular interest because it is really looking at how you could make use of new distributed energy resources to provide system services and guarantee security. Now, what does it mean? Again, just to put it really in simple terms, Instead, if you are able, for example, with your batteries that are installed at home, or maybe larger scale batteries installed at the distribution network level, of course, you can do this at transmission network level as well, can you inject energy so fast, the so-called fast frequency response, as to bring back the frequency response from this curve to the blue curve? Of course, that's not how the mathematics and the physics works, but it's really just to give you a little bit of a simple idea. So if the problem of inertia is we are losing the very fast response of synchronous generators to come automatically, can I replace this very fast response with, for example, battery response? Of course you can. However, you need to be able to model this properly first, and then you need to be able to demonstrate this properly, because the response is fundamentally different. And in fact, it's no problem. I would solve all the problems, and indeed, it's done it in a way. But there are big things that batteries can do. And for example, to share an example of how community energy systems that are aggregating to virtual power plants could provide, for example, a fast frequency response in general participating in frequency control ancillary services. However, there are issues with that again are associated to the market. What are these issues? Well, it's the fact that there is a limit to everything you can do. So in some work that we're doing now, for example, we're showing, first of all, how the fast frequency response compares to primary frequency response from batteries. So if batteries are providing services according to the current market mechanism, or actually we introduce a new market mechanism for fast frequency response, what the system benefits are in terms of cost savings, and then how these savings would change in terms of saturation effect. Now, let's focus on these cost benefits. This study is done for the UK, future scenarios put forward by National Grid. What we see here is, for example, that for 2 gigawatts of batteries in a system with 60 gigawatts peak, if you only use the batteries for energy balance, so energy arbitrage, actually the system benefits, these are system cost reductions for the overall system, system benefits are very small. If you now use batteries to provide primary frequency response according to the market rules, now these benefits increase a lot. So effectively you can save lots of money in the system. If the batteries can react very, very fast, so say in 0.5 seconds, now the benefits are a lot bigger. So effectively you should use the batteries, as is being done now in South Australia, to provide fast frequency response, because this is really bringing system benefits. However, as you can see, when you increase the penetration level of batteries, the cost function, system benefits change significantly, because now the impact of very fast response as opposed to just primary frequency response changes, and most important, there is a sort of saturation effect. So if you wanted to translate the system cost benefits into, for example, cash flow that would be available to market participants, obviously, for 2 gigawatts in here you can save 1,000 or whatever it is measured unit is. For 10 gigawatts you can only not even say double. So the specific cost per installed capacity is a lot. Specific cost reduction per installed capacity is a lot less. So there is clearly a saturation effect that again you're seeing in the market. Because I want to show you this one, which looks at the ability of not only batteries to provide this fast frequency response, but other resources too, particularly load resources that can be flexed very, very fast. And a typical load that could do this is electrolyzer to provide, to generate hydrogen. So in other ways, can I use renewable? First of all, can I use renewables to produce hydrogen so that I have zero carbon fuel? And then because this is a load that is very, very flexible, I can switch on and off this load in less than half a second like batteries. Can I use this load response to provide fast frequency response? And how is this compared to battery response? So when you put in a system model, you will see that the model automatically will tell you what you should do with the hydrogen and what you should do with batteries. And there is, yes, competition between the two, but there's also complementarity. So for example, you will see that with hydrogen, you should do the negative frequency response, so due to negative frequency drops, whereas the batteries should actually be more used for positive frequency response, or for high frequency response. So the two are complementary technologies. On this basis, actually, we are doing a number of projects around Australia, particularly this in Port Lincoln, which is the end of Denham, which is an area that is very, very constrained. Here, the Kaltana substation, which is what connects Port Lincoln to the rest of Denham in the Eyre Peninsula, South Australia. This is very congested, and there are more and more inquiries for connections of PV and wind. At the same time, there is a great potential for production of hydrogen that you would like actually to export, possibly as ammonia, for example, to Japan and Korea. So once we have this, can I actually use the hydrogen that I'm producing here through these electrolytes to also provide fast frequency response? Because otherwise the Office of the Technical Regulator in South Australia would say, you want to connect, you also need a battery to provide fast frequency response. So could these new renewables actually contract with the electrolyzer to provide the required fast frequency response? So we're looking into this, and again we're building the operational maps of, for example, the Port Lincoln area, looking at the ability of the system under different conditions to provide different services to the rest of the transmission system, including 6 seconds, 60 seconds response, and possibly faster response equivalent to a battery. Then this is sort of projects that are in a way still the modeling stage. What we're looking at is also to actually do a little bit also our bit, so try to build a virtual power plant also in the university campus. So actually we could use resources in the university to demonstrate the modeling and the operation of distributed energy resources as a virtual power plant, and that's how for example, the PQ map of the campus looks like. The moment that you use, you put in there batteries to provide fast frequency response, PV with inverter flexibility, and these are gen sets that you could also switch on if required. So based on sort of view of using more and more distributed asset to actually demonstrate it in the campus of the university, step by step we say we would like to install this in the Parkville campus, and we are just bidding for a project with the Victorian government to do that. Next, we would like to do it in Fisherman's Bend, where we are building the new engineering campus. There will be $1 billion investment there. So since $1 billion has been spent, can you actually also build a small synchronous, well not so small, synchronous machine in the centre of Melbourne, since you're doing from scratch? So as to think of a sort of network of virtual power plants. And then say, okay, how much can we scale it up? So we take the system plan, the integrated system plan, say, okay, we all have all these renewable energy zones that, and somehow they will need to be balanced in some ways. So can I use actually all the load flexibility that is available or might be available in the future to balance renewables? And a project that I was preparing when I came to Melbourne, for which I got a VESCI fellowship from the Victorian government, again, before I could understand actually what's going on here in Australia, was about saying, well, it's expected that this would arrive sooner or later. So why don't we use the whole city as a flexible load? So we move from saying distributed resources, campuses, now we start aggregating more and more loads, and we use the whole city. So we are in discussion with the Minister of Energy of Victoria actually to have a number of precincts around the city of Melbourne to actually be able to be aggregated and provide system services to AEMO and participate in the market, so also improving the business case. In fact, the business case is critical. You must be able to understand how by playing in these markets, you also create an opportunity for new distributed energy resources, because because again, if you have a genset that is not used, or a battery that is only doing, for example, energy arbitrage, that's probably wrong, because the value is in something else. And the idea is, can you manage to understand where the value is and stack up all the different revenues from provision of different services? The frequency control ancillary services, but also a number of other services. So I am concluding again by stating that if engineers built, what is this? Large Hadron Collider, yes, it's great. So if engineers build Large Hadron Collider, again, that is able to simulate, replicate the Big Bang, again, there is big magic that engineers can do. However, they need to be as smart as this guy. Who is this guy? You haven't met him, I guess. This is Thomas Edison, yes. So Thomas Edison said in 1878, we'll make electricity so cheap that only the rich will burn candles. 1878. Do you know when Maxwell wrote his equations?
1967.
Yeah, 10 years before. So we're talking about the fundamental equations were written 10 years before. And by the way, the equations that we know them now were written probably 5 years before by Cavendish. Maxwell equations were like 100 pages of complex equations. So basically electricity didn't even exist in the physics. So how can you build something that doesn't exist? However, he did it, he did quite well, because then in 1882, he decided to build electricity by saying, opening up the first power station per street, and then the power distribution system and so on. Why did Edison do that? Why did he do that? What is Edison famous for? Light bulbs. Okay. That's exactly the point. So I patent light bulb, it's fantastic. I would like to sell this. There is a problem. These light bulbs are powered by electricity, and electricity does not exist. let me invent electricity so I can sell my light bulbs. And in fact, what he was selling, of course, he was not selling electricity. What is electricity? You go to Manhattan in 1882 and say, do you want to buy kilowatt hour of electricity? Or say, just do you want to buy my light bulb? Forget candles. You don't risk like fires and so on. These are absolutely safe. You buy the light bulb, I will give you electricity. So it's really energy service company business model. You buy the service, I'll do the rest. You don't bother with kilowatt hour. By the way, Edison was saying, you buy light, I also give you heat. Because it was co-generating the power that was discarded by the thermal prime mover, and actually was also giving heat for free. So pretty smart. So that's what I'm saying. You need to be this smart in terms of understanding technical issues and, most important, the economics of the system. You really want to penetrate into any kind of market already when we actually built the very first power station. And, there was another big guy against Edison at the time, Tesla. We still have a Tesla today, it's a different Tesla, but he's in a way doing very similar things. And that's why, in a way, I appreciate him, because of sort of visionary thinking and the ability of actually penetrating, disrupting markets. So to conclude, the idea is that there's lots of exciting things that are happening in the system, which requires new tools really to address the energy trilemmas, and probably associated with these new tools be new markets and market requirements that would be needed, because there is no really technical aspects that today go without economic aspects and business case. And if you are interested in all this, I am starting a new SIGREM working group that's called Flexibility and Grid Services from Distributed Energy Resources. It will be announced at SIGREM Paris this August. So if you're interested in this, you're most welcome to join, where we will look more and more into sort of aspects that I was presenting. And then I leave it to you to think if it was the Black System event was a reliability event or was a resilience event, defined as low probability, high impact. And actually, if we are supposed to worry about resilience events, or actually we should focus more on sort of credible contingencies we've done so far. So lots of philosophical questions, and there are more and more discussions, of course, and so on. And with this, I conclude, and of course I welcome questions either now or later, or you can just run me an email to one of my 2 email accounts. Thanks a lot. Thank you very much for your attention.
Do we have time for questions? So I'm sure you should have questions.
I'll ask a question. So you mentioned the use of hydrogen generation as a potential sheddable load, I guess, in this scenario. Would you shed that load in an instant, straight away, or would you want to ramp it down in some controlled way to achieve your frequency control?
So is it what electrolyzers can do, or what the system should do?
Or what would you like to do?
All right, okay, so there are 2 different aspects. So there are constraints in what the electrolyzer can do. This depends on technology electrolyzers, but there are some very fast ones based on PEM, basically, that can do it pretty much almost like a battery. And in fact, that's the only technology that in the fast frequency response market of National Grid in the UK is allowed to participate together with batteries. So there are only batteries and subtile electrolyzers. From the system perspective, this is something that is more about sort of system study, which is about what fast frequency response would you like to design. So the 6-second requirement today is coming probably from experience and simulation. Say, looking at how generators perform, looking at the sort of events we have, 6-second response on average works well. The moment that we introduce a faster and faster response, what will happen to the system? So in a way, the mathematical models that we developed are actually exactly to address these kind of questions. What kind of new requirements you need to introduce in the design of the frequency response characteristics and markets to have, in all cases, a response that is stable and desired. I do not have a direct answer, but I say we have the tools at least to do this analysis. Actually, this is a big topic. I would say it will be a big topic for the next probably 5 years, not only here, I would say.
So my question is in relation to markets, which certainly here is the favoured way of getting sort of electricity assets built. I wonder if you have any comment on the sorts of changes that the things you're talking about would require in the design of markets, and whether our current market institutions are able to sort of deliver those in a timely fashion, and whether there's any learnings we can take from other jurisdictions.
Yeah, so certainly that is again very, very big and important question. It's very hard for markets to keep up, I'd say, just to be honest. I mean, it's very hard for system operator, as you know, to keep up with the changes, but markets is even worse, because it takes lots of time to actually adapt and so on. So in their defense, it's pretty complex, I would say. However, certainly there is a requirement to understand that because the technical characteristics and environmental system are changing, also markets have to change. So there is, in some jurisdictions, there is a view that the market rules. If some technology, for example, does not work in the market, technology doesn't work. No, actually, it's not the opposite, but no, almost. You need to understand how to actually design the market so that you allow the best technology to be able to penetrate the system. And that's why, in a way, in the models that we use, we also base our analysis on fundamental cost functions. They should be reflected in an ideal competitive market. Because when you look at fundamental cost functions, then you will also understand that, okay, actually, batteries can play a role, electrolyzer can play a role, and so on. And then you look at the market and say, but why don't I see, for example, batteries participating in, say, capacity markets, for example. And then you learn, but I need to provide a peak requirement for 12 hours. what is the reason to be there for 12 hours? Of course, no, a battery cannot participate in a capacity market. You must stay there for 12 hours. So, is it the market or is the technology there? Right? You know the answer. So that's in a way how, sort of research and thinking we should have. But again, as I said, it's hard for markets to keep up. But the moment that policymakers, regulators understand there's a need to reform all of this because the system is fundamentally changing, well, then I'm sure that it will also push for an updated market. And this is already happening. I mean, there are lots of discussions listed in NEM about, for example, day-ahead markets, maybe capacity markets, and this.
With the graph you had earlier with the 3 constraints basically and the nice red curve, the nadir, if some of the primary frequency response was replaced with, say, fast frequency response,
yeah.
How would that shift the red line?
Yeah. So again, we have, I don't have a picture here, but yeah, I mean, I don't have the picture here, but we have the pictures. Effectively, it would just basically enlarge we'll just change basically the secure area, yes. Because effectively what you have is
Does it shift it left sort of thing, or?
It's more complex. It's more complex than that because the batteries react in a sort of impact in a non-linear way on the thing. So it's not exactly shifting and so on, but it changes a little bit the shape.
But it makes the secure area larger.
Yeah, effectively that's what it does. Because it effectively means, sorry, that you require less of the 6-second response if you have some other response that is injected very fast in the system. Then how it does it exactly, it depends on the system and the characteristics, but effectively it makes it more secure.
How is the coordination done between the high inertia and low inertia system?
How is it?
Coordination done when the system requires to shift from high inertia to low inertia?
Well, I mean, effectively, it's not that the system really changes. It's just identifying the fact that if, for example, we're talking about bidding, let's forget the bidding. If we talk about the fact I need to, as a system operator, I need to say to the market, I need this much frequency response. I then understand the fact that if inertia is until here, I need this much frequency response. The moment that the inertia goes more down, I need more frequency response. It's really, in a way, I haven't thought of this too much, but from a market perspective, it's really identifying now that there is a function to define how much primary frequency response you need, which depends on the level of inertia for the system operator. Now, how this is put out in the market is less straightforward because the market is also bidding for energy and all that. That's why in a mathematical model, you do it as a full co-optimization of everything. How you translate that into market mechanism, that is challenging. So I know how I can translate that into dispatch engine, but then how you can translate this fully into market mechanism is a little bit more challenging.
You talked about turning cities into virtual power plants. How would that exactly work? Would that be using batteries or demand side management?
Yeah, it's all of them. So effectively, you look at the future. I skipped a few slides because I was taking too much time. If you look at a future where you would like to decarbonize the whole energy system, electricity is still just a tiny bit. You need to be looking at more transport, to be looking at heating. In Melbourne, there is quite some heating in winter. So how do you decarbonize that? So the moment that you see that we have more and more electric vehicles that effectively are mobile batteries, the moment I have more and more electric heating, and there is lots of thermal inertia in buildings, in water tanks for hot water and so on. All these are very, very flexible resources. So can you switch off water heater instead of introducing a battery? we did the studies during the thinker review, and you would say that the benefits of switching off large air conditioning systems, if you can do it as fast, almost as fast as batteries, are pretty much the same. So do you really need to invest into all these batteries when in the future you know that there will be other sources of storage, can be virtual storage again, and be able to provide similar services? Of course, again, this is also goes with the business case opportunities and all that, but in principle, there are lots of potential, there's lots of potential flexibility that you can untap from other energy systems. So it's really not only batteries, it's everything you said, demand side, electric vehicles and all that.
Using your mathematical equations to derive characteristics of inertia from other types of generation, do you foresee a future where you have no synchronous generation whatsoever?
Well, the mathematical modeling doesn't work at the point, because it's still a sort of phasor-based model, if you look at that. So the moment that we actually go towards very, very low levels of inertia, I don't think anyone knows what will happen. And in fact, if you look at the recent publications from IEEE about the system strength, what modeling you need, PSSC is not sufficient, the PS card, so you need to look into electromagnetic transient dynamics and these kind of things. So that, in a way, is telling, although you do that by simulation, in terms of mathematical model, say the mathematical model starts faltering a little bit at that point. This will be next stages that we will see later on.
So this will give us some more longevity out of the current arrangements for the power system and generation mix?
Yeah, I would say, they probably, I mean, from our analysis, I would say that at this level, probably you will not see really big changes in how you need to sort of write equation and so on, until, say, 20%, even 10% minimum inertia level. So out of 100% you have now, say if you really go down to say 10 or 20% inertia level, then at that point you start need to be a little bit worried. But this is system level, talking about region, for example, talking about Victoria and so on. If you look at individual small areas, for example, weak networks, where you see you don't not only have the active power, the frequency, also have the voltage and so on, I think already with smaller penetration levels you start seeing problems. So this is really to provide the high level analysis and maybe to sort of implement this for market purposes. However, then there will be a lot more detailed technical analysis that is required, especially when you go into weak areas, I would say. And IEEE was well aware of this. I already seen it.
I've got quite a lot of questions, but one of them would be, is the IEEE working on a control protocol? Because when you talk about making virtual power plants, and then another tool is islanding and having that microcontrol itself until it can rejoin, etc., then what you're talking about is a SCADA protocol and a new control protocol. So you're almost going to say, well, we need to invent our own IP, don't we? We need to make a new internet protocol that says you can drop this on any system, and then you tweak it and you build layers across over top of that. So is that what IEEE is working on now?
Yeah. The answer is I do not know, but I would expect that there are working groups that are looking into this. I can tell you that SIGRO is certainly looking into this, and including the new working group. There are 3 working groups in parallel on sort of topic. We'll also look into this kind of protocols. I am sure that IEEE is also working on similar aspects. Maybe they're not calling virtual power plants, but no, similar aspects. Certainly this is a problem that we see today in Australia, because the moment that you want to talk to different people, just understand what they mean by virtual power plant, what they can deliver. Are you really sure that you can do the 6 seconds response? Oh yeah. Well, no.
Yeah, it seems fairly obvious to me that if you ask Dean to solve this problem for the WEM, which is trying to think of what the rules look like, the technical rules, the market rules, the connection, that of course Dean will try, and so will the WEM, and so will every macro and micro grid operator. Eventually what will come to fruition is a universal protocol that they can apply
Easy.
to, eventually.
Yeah.
So it seems like we'll struggle for the next X number of years until something like IEEE publishes a protocol that can then be adopted by whichever network operator.
I think you're absolutely right. Probably the two things go together. I mean, we know that there will be a point where the sort of we understand more and more the technical problem. In parallel, to deliver on that technical understanding, we need this kind of protocols. Absolutely.
I've got maybe a naive question. How hard is it to do that, working out what that frequency response security map looks like for a system like ours?
It's very simple. It can be done in minutes.
But writing the rules and building the system is different.
I guess you agree. Yeah.
Okay, so the equations that pop out at the end of that you might build into your dispatch engine are fairly simple in their form?
It is a simplified model, of course, but yes. Yeah, I mean, that's why the interesting part of having an analytical model is that you have an equation, just put in the numbers, and you got the results. And you don't have to simulate, you don't have to do anything. And the big work down there was actually modeling analytically, because that was never done before. Because then once you do it analytically, then you can do all the maths. It's okay, now I simplified, I put into dispatch engines. You can't do that. Yeah? There's no way that you could incorporate this kind of constraints into the current system equations. What you would have to do is run an OPF like it's done today, then give it to a simulator for dynamic assessment, so it can be PSCC, PSCAD, DXILET, and then iterate. That's what people have done. It's impossible to do it really as a sort of robust model for this market, real-time market analysis.
Okay, and so Dean will already know the parameters of what's the lowest nadir he can tolerate and rate of change.
That's actually an input, so actually you can decide what you want and say, okay, at this time I accept, for example, 49 Hz, at this time I want to be more secure, 49.5. You just change the parameters, and in real time you can just define this every 5 minutes, like in the net, every 5 minutes you can generate a new map with your new desired parameters, and through your dispatch you will know exactly if you are secure or not. And if you were to implement what we propose, it will always be secure, in principle.
So then can you know what that looks like kind of characteristically over time? So if you're going to do investment analysis in new technologies, for example, can you describe over a period of years what those constraints might look like, for example?
Absolutely. I mean, that's, effectively, again, back to the integrated system plan. We're looking at developing planning models where you have very detailed operational constraints. So effectively, when you plan for new technology, you know that technology is actually optimally planned, considering all this kind of real-time operational constraints that we have to deal with.
I'm just conscious of time. I think the message will be that in the very near future there will be another constraint, which is inertia here. And if you're a consultant, you know there is a lot of renewable generation that are going to add to this system. So inertia definitely will be a constraint to be mindful of. We are working with the industry on a set of generated performance standards. In their own benefit, it will be to consider those standards and avoid constraint in the future. So I would like to thank you, Pierluigi. I think you spoke tonight not only to the engineer in the room, but also to the economist and to the regulator and to the lawyer in the room. So thank you so much. I really enjoyed your talk.
Thanks so much. Thank you so much. Really appreciate it.
So thanks very much for attending this event. So IEEE organizes a few events like this during the year. We'll keep you interested. Please leave your details here and we get you invited. Thank you so much and have a good night.